Today, we are going to take a look at some of the new questions that I have populated on the database. But I will give you an opportunity for next week if there are areas of review throughout the course that you want me to go back again to. I will be able to give one last lecture or tutorial on that. Today, question 7001 says it's for spherical coordinates rho, theta, and phi. Position vector rho, e rho, which is a function of theta and phi. One of the following statements is false. Phi is equal to constant in cylinder. Rho is equal to constant in a sphere. Theta is equal to constant in a cone. The position vector differential is the rho e rho plus rho d theta e theta plus rho sine theta d theta e phi. So you already know that A is the correct answer. That is, the false statement is that phi is equal to constant is a cylinder. So I want the class to go online and tell me what kind of surface that is. If it's not a cylinder, what kind of surface is it? Phi is constant. What kind of surface is phi is constant? Ola Lekon, you are wrong. Ola Lekon, you are wrong. It's not a sphere. Philomena, wrong. I'm still waiting for more participants to respond. Why? What is phi is the constant? The people who have responded have given wrong answers. Why is it? That is the correct answer, that is an error. It's not a cylinder. Well, let me see whether I can show you something here. Because since you are all in error, I better show you. So if you go to Wikipedia, that's the easiest way to get this information. And you go to spherical coordinate. Okay. What you see, I just want us to see the inverse transformation because we are always looking at the direct transformation. Inverse transformation is that phi is the arctangent of y over z over y over x. Okay, so let me create a new page because this is very important. Let me add a new page here. Okay. Let's go back to our slide projection. You see, the transformation, if you want to go from the rho theta phi back to xyz, this is the transformation. So if theta is constant, that means that y over x, that's the arctan of y over x is constant. That also means that y over x is constant. And that can easily be seen to mean that y, the equation is where is it now? Y is equal to x plus constant. Now, class, I want to ask, what kind of equation is that? Because if phi is constant, tan y over x is constant, that means that y over x is set. For the arctan of y over x to be constant, that means that y over x is set, must be constant. If y over x is equal to constant, oh, sorry, I'm wrong there. So it is more like this. Because if y over x is constant, then y is equal to cx. What kind of equation is that? This new thing. What kind of geometrical object is it? Okay, somebody said, Chris Oluwatomiwa Ikunife knows that is a line. It's not just a line. It's a line that passes through where? That's a line that passes through where? That line passes through where? It passes through the origin. Okay? Because it passes through the origin, when you now take that, when you now look at that in 3 dimensions, what do you get? That is a plane passing through the origin. That is a plane passing through the origin. So because no matter what value of Z is, that is a plane passing through the origin. For every Z, it is a plane. So the correct answer there, where for that not to be an error, phi is constant, is a plane. You could also see this by going to look in our previous work. If you look at the spherical coordinate diagrams, you will remember that the phi is equal to constant is a plane. So in the spherical coordinates, you have a plane, a sphere, and a cone. So phi is constant, it's not a cylinder, it's not an ellipse, it's not a cone, it is a plane. So that is it. Now, the position, why is this one not wrong? The position differential, the position vector differential. Why is that not wrong? Can somebody explain to me how we get these 3 vectors when there is it's only one vector in the position vector? The position vector for spherical coordinates is just rho, e rho. How did we now get e rho, e theta, and e phi in the expression for the position vector? Why is this not wrong? I want people to go to the chat room and tell me, why is that not wrong? Because only one statement is false. Why is it only the first statement that is false? Of course, rho is a sphere, is correct. Theta is constant, is a cone. E rho is a function of E, is a function of E phi and E theta. E rho, no, E rho is not a function of E phi and E theta. E rho is a function of phi and a function of theta, not a function of E rho and E phi and E theta. Sadiq, take note. E rho is a function of phi and a function of theta. It's not a function of E phi and E theta. No, they are independent. Why is this correct? Why is this expression here? How did we get all these other additional expressions? Can somebody tell me? Because some people are interested in guessing. And I don't think you will do well if you are depending on guessing. I don't think so. So, guys, I think you will do well. You will do better if you know what you are doing. Why is D not wrong? Well, it's already 14 minutes. Time is not on my side. So let me just go through. First of all, R is equal to rho, E rho, which is a function of theta and phi, because E rho is sine theta cos phi plus sine theta sine phi plus cos theta. That is why we say it is a function of theta and phi. This is the full expression. It's a vector of I in ijk. So if you differentiate this with respect to rho, all you get, because it's a linear function in rho, so all you get is E rho. If you differentiate it with respect to theta, you can see this is the only thing that can be differentiated here, because cosine, everything else remains unchanged. This is the only thing you can differentiate here, because cos, everything else remains unchanged. And if you differentiate with respect to theta, you have minus sine. That is what you have here. And what we have in this bracket is what we define as E theta. That is where E theta comes from. So you can see that by differentiating this R, you get rho E theta. That is where it comes from. If you differentiate the same thing with respect to phi, you are going to get, if you differentiate with respect to phi, because this is cos phi, you are going to get minus sine phi. So that's why there's minus sine phi here. If you differentiate this again, with respect to phi, you are going to get plus, you are going to get cos phi. So there is an error here for me. So let me just correct that quickly. This is negative. Okay, so that is what you have. What you have in the minus what you have in the bracket here, if you take the sign out, you have minus of sine phi I minus cos phi j. That is what we define as E phi. So E phi is minus sine phi I plus cos phi j. Now, let me just go to where that full expression is. Now, so we can therefore take the expression R, which is rho E rho theta phi, as simply a function of rho, theta, and phi. It's a function of rho, theta, and phi. And if it's a function of rho, theta, and phi, from the law of partial derivatives, the differential element, dr, is written as dr the rho plus dr the theta plus dr the phi for a function that is a function of three independent variables. I'm sure you know this formula. Now we already know that the r the rho is E rho. We already know that the r theta is rho E theta, and we already know that the r the phi is rho sin theta. That is where these expressions come from. These expressions are not just guesswork. Now, the next question I'm going to ask you is, why would it be an error to say the r is equal to E rho the rho, E theta the theta, and E phi the phi? Quickly answer that question. Why would it be an error? Just looking at this, why would this be wrong? This is correct. Why is this wrong? Apart from the fact that that's what we derived, can you just looking at the last expression there? Why would that be seen as immediately wrong? The participation in class this morning is very poor. The attendance is poor, and participation is even poorer. Here, E theta, if you look, E theta on its own is this quantity. E theta is just cosines and sines. It's not a length. It's just cosines, dimensionless, cosines and sines. So you need this for dimensional consistency. We need an element of length to multiply it. Similarly, E phi requires an element of length, and this comes out immediately, dimensional consistency. So this comes out immediately when you do the differentiation correctly. It comes out. So that is the reason why this is wrong and this is the right thing. So the question is, where did this come from with this single expression? It comes from the total differential of the R. If you get the total differential of the R, you are going to get three partial derivatives because it's a function of three variables. And that's where these expressions are coming from. So whereas the position vector itself is a single term, the differential is three terms. That's where they come from. And they come from this, the differentiation there. The R is dr the rho, dr the theta, dr the phi, which gives you this. After computing dr the rho, which you computed here, that dr the rho is E rho, dr the theta is rho E theta, and dr the phi is rho sin theta E phi. So the next thing we are going to do, we are going to find the surface area vector factor. You remember from when we were dealing with Green's theorem and Stokes' theorem, we found the area. In Stokes' theorem, we find the area vector. You know that when you differentiate the position vector with respect to the two parameters on the surface, you are going to get the vectors on the surface. And when you take the cross product of those vectors, you are going to get a vector perpendicular to the surface, which is obvious because E rho is perpendicular to the surface of the sphere. So that is, but there is this scaling factor is what you are looking for. So you can get this scaling factor by simply remembering that theta and E phi are in an orthonormal triad. They are part E rho, E theta, and E phi are part of an orthonormal triad. So E theta cross E phi is E rho. But if that is very hard for you, you can go by direct computation, remembering that E theta is this quantity here, and that E rho and E phi, again, there's an error here. Let me just correct that error. E phi is, this is negative here. Fortunately, the computations are correct, so walk through the computations, so don't worry about that. So if you have this now, you will see that if you now take the cross product of this bracket, of this row times this bracket, times minus this row times this bracket, and you open the bracket, noting that I cross I is 0, I cross j is k, j cross I is minus k, j cross j is 0, k cross I is j, and k cross j is minus I. If you do all of that and you open these two brackets, you will find the same answer that you could have obtained here. It is easier to obtain it here by just remembering that E rho, E theta, and E phi constitute an orthonormal triad. And so if you do E theta cross E rho, E phi, we are going to get E rho, and the multiplication factor remain unchanged. So, but if that is hard for you, go through the long process of working it out, and you get the same answer. So the scaling factor for the surface vector on the sphere, where rho is constant, is this quantity here. We've already looked at the position vector differential, which is which is obtained by differentiation. It is not a guesswork. It's not an arbitrary thing. Every term there can be accounted for, and they come from the partial derivative to total derivative of the differential that you have there. And it's also, again, it's also the first step of the Taylor series expansion of the function of three variables. So there are so many ways you can look at it, and we've done it in so many ways. You get the same answer. The above arguments make the next question straightforward. For spherical coordinates, rho, theta, and phi, the position vector differential, the R is this. So that is what we have just been talking about. So you see that if you see this in an objective, this will not be right. You will be tempted that since position vector is rho e rho, that the differential will just be rho d rho e rho. It is not. It is simply d rho e rho plus rho d theta e theta plus rho sin theta d phi e phi. And we have spent some time at the earlier part to actually go through with this computation. This is a question already on your database, so you might face it in a final exam or in your self-test. So now, what is the surface vector on the cone? The surface vector on the cone, because on the cone, theta is constant, so we cannot differentiate with respect to theta, but we can differentiate with respect to phi, and we can differentiate with respect to rho. When we differentiate with respect to phi, we get rho sin theta e phi, and we differentiate with respect to rho, we just get simply e rho. If you take the cross product of the two, you know that e phi cross e rho is equal to e theta. That is because, again, these three of them are in an orthonormal triad. And then, so the final factor is rho sin theta e theta. We can also get it by direct computation using Cartesian representation. If you use Cartesian representation, sorry again, this function is copy and paste here, so it's been error everywhere. So this is this here is in this particular case, the minus is here. Okay. Am I right? No. If okay, the phi. Sorry, I have a bit of a mix-up here. The R the phi, we computed that before. What is the R the phi? And okay, so that is now correct. So this is the R d phi. The first term here is the R d phi. So what I'm saying is that you can get this directly by remembering that E rho, E theta, and E phi are in an orthonormal triad. So E rho cross E theta will give you E phi. So it's only rho there. That is it. So, but you can also do it by direct computation by looking at this thing in the Cartesian coordinates, the R the phi is this quantity and the R the rho is this quantity. If you take the R the R the rho, let me just be sure that the R the rho code that I have here is correct. Let me just go back again. The R the rho. Oh no, the R the rho is just E rho. So I'm sorry for the mix up here. The R the rho is E rho. Okay, the R the rho is E rho, which is this one. Okay, so this is correct here. The R the rho is correct here. So if you work it out on you can see that it's now rho sine theta E theta. The other one was rho squared sine theta. So this one is rho sine theta E. So this one is rho sine theta E theta. So just notice. So if you are cramming, you are going to get into some problems. So this is rho squared sine theta here, E rho, whereas the other one is rho sine theta E theta. So let us look at the surface of the plane. The surface vector on the plane. You now know that constant phi is the plane. The surface vector on the plane again is the R the rho cross the R the theta. That is the multiplication factor there. So if you have that, you will see that there is no sine or cosine here again. So you just have rho E phi because E rho cross E theta is E phi. We can get this simply by doing this multiplication here. E rho cross E theta. So that is it. So we can get it also by direct. You can get it by direct computation. You can get it by direct computation. So if you want it by direct computation, I can see there's an error here. Just go back to the first. I don't want to go back to the first page. We computed the R the rho. We computed the R the theta. Compute those two and multiply them out using the Cartesian representation. I will correct this before it's posted today. So following the same argument, the position vector is differential element and area as well as area vectors are easy to compute for both Cartesian and cylindrical coordinates. We have done this now for spherical, which is the most difficult of the usual coordinate system to use. But for the other ones, the results are simpler. So you can easily get the other ones using the same argument. What arguments are you going to use? You are going to start from if it is cylindrical now, can somebody write for me if it is cylindrical, what would be the position vector? Write it on the chart. Where are you going to start? What will be the position vector for the cylindrical? So this is the position vector for spherical. What will be the position vector for cylindrical? Where are you going to start from? Okay, so Samuel Oketola, you are a guy with curiosity to everyone, you are right. RER plus ZEZ. So again, what you are going to do, you are not going to have the R is equal to the R, then the R, the theta, then the R, the Z, the Z. If you compute using this, if you use the correct position vector to compute the differentials, you are going to get the correct differential for the cylindrical coordinates. The case of the Cartesian coordinates is trivial, but still, I want you to tell me what will be the position vector for Cartesian coordinates. Write it on the chat room. I'm watching it on my own screen. I'm watching what you type on my own screen. Cartesian coordinates. Waiting. RIEI. Well, I don't want the shorthand. I want you to write it out in full. Nathan, I know what you have written is right, but I want it in full. You are using the summation convention. Yes. Samuel Oketola, you are wrong. It's not E1 plus E2 plus E3. It's XE1 plus YE2 plus ZE3, or XI, YJ, and ZK. Okay. Tolu Odunlami, you are right. Tolu. Then Anasi Chigozi, you are also right. X1 E1 plus X2 E2 plus X3 E3. If you go through the same the interesting thing is that if you go through the same differential operation here, you are going to get the correct thing. So this is a method that will work for Cartesian, for cylindrical, for spherical, for prolate, or for prolate spheroidal, for parabolic, cylindrical, for any coordinate system, for elliptical, whatever the coordinate system, this differentiation here will always work. It will always work. So this is what I want you to be using rather than guesswork or assuming that everything will work like the Cartesian. The Cartesian will work here and other things will work. But if you just start with the Cartesian, you stay there, the other you are going to get wrong results for the other things. Okay, so that is why I said here that every computation we have done so far for cylindrical, it will come in your test or exam. So I can give you Cartesian, I can give you cylindrical, and I can ask any of the questions I've asked. I can ask about what are the surfaces. You may not. And can you tell me what are the surfaces in cylindrical coordinates? What are the three surfaces in cylindrical coordinates? Can you write it out? Because it's in another question that I didn't bring out now. What are the three surfaces in cylindrical coordinates? What is the surface? R is equal to constant, theta is equal to constant, and Z is equal to constant. Cylindrical coordinates, R is constant, what surface is that? Theta is constant, what surface is that? Z is constant, what surface is that? Z is constant is cylinder. G Olalekon, you are wrong. Z is constant is not a cylinder. Sadiq, R is constant is not a circle. Remember, you are not in 2 dimensions. If you are talking of polar coordinates in 2 dimensions, you'll be right, Sadiq, but you are in 3 dimensions. And that is, I will give you that answer and you quickly pick it and you miss that question. So Sadiq, learn from that. Oluwatobi, R is constant is not a sphere. Oluwatobi Aliu, R is constant is not a sphere. In spherical, rho is constant is a sphere. In cylindrical, R is constant is a cylinder, not a sphere. R is constant is a cylinder. It's not the base of the cylinder, it's the total surface of the cylinder. James Udoton, it is not just the base of the cylinder. It will be the base of the cylinder in a 2-dimensional cutting through it. A guy with curiosity, Z is constant is a plane, you are correct. You are curiously correct, the man with curiosity. Okay? Curiously, you are right. So what about theta is constant? What kind of surface is theta is constant? What kind of surface is theta is constant? So you have talked about R is constant. Ebere, you are guessing. You say it's a cone. Theta is constant is not a cone. Theta is constant is not a cone. Theta is constant is a cone in spherical coordinates. In cylindrical coordinates, it is not a cone. You see, you will see guesswork is going to land you in hot water. Theta is constant. The curious man is curiously wrong in this case. Theta is constant, it's not a cylinder. Now, again, go and look. Tolani Ade Penro, I think theta is constant is a plane. In cylindrical coordinates, theta is constant is a plane. Again, the easiest way to find that out is to see what the inverse transformation is. The inverse transformation here again is arctan y over x, and it's a plane. So that is a very simple question that you will answer quickly and you answer it erroneously because you have not thought about it. So in cylindrical coordinates, theta is constant is a plane. Now, the last question before I move on, can you tell me what the surfaces are in Cartesian coordinates? The surfaces x is constant, y is constant, and z is constant. What are those surfaces in Cartesian coordinates? Okay, curious man says they are all planes. Good. All of them are planes. So that is correct. So let me take you through something that is a little bit more challenging, because the examples have been given are easy. Okay. The transformation coordinates, the transformation equation for, let's see, let me move this away. The transformation equation for parabolic cylindrical coordinates are x is equal to xi eta, y is equal to half of xi squared xi squared eta squared, and z is equal to z. Therefore, the parabolic cylindrical position vector is A. The correct answer is A. The other answers are wrong. But since I've already showed you that they are correct, I've showed you the correct answer. Now tell me why that is the correct answer. Go to the chat room and tell me why this is the correct answer. How can you get that? If I introduce a coordinate system you have never seen before, you have never seen this coordinate system before, but I give you the transformation equations, and I'll tell you now, tell me the position vector. Can you get it? Can you pick it from a list? Can you pick the correct thing from a list? How will you know that A is the correct thing? Go to the chat room and tell me how it is that A is the correct answer to this question. Good. Samuel Oketola understands that you go back. If you have the Cartesian transformation, then you express it in Cartesian. And when you express it in Cartesian, you can see that since x is xi eta, and y is half of xi squared minus eta squared, and z is z, that is x e1 plus y e2 plus z e3. Simple. So simple. So simple. And that is how we compute even the spherical that we got into rho e rho. This is how we started. This is how it started. It is the definition of e rho that made it simpler than this. So this is the correct thing, because we are going back to the Cartesian, since we have the Cartesian transformation. So it is easy to get this, the coordinate system must be consistent in all coordinates. So if you know how to get it in Cartesian, get it in Cartesian with the value of x, a value of y, a value of z. Can you explain again? There is nothing to explain. Go and ask Israel, allow you. You know that x e1. What is x? X is xi n. So instead of x now, write xi eta. And then instead of y, write half into xi squared minus eta squared. And instead of z, because this is the transformation equation for x, y, and z. Ike Okoro Chibuke. Can you see what I'm saying? Because you know that the position vector for Cartesian is x e1 plus y e2 plus z e3. So you know what x is, you know what y is, and you know what z is. In this new coordinate system, just write it out. Simple. Ike Okoro, can you acknowledge if you have, if that is clear to you now, because you are the person asking the question? Okay, so Ike Okoro, you see that the expression in Cartesian is easy. So if you have the Cartesian transformation, then you have no problem getting the position vector in any coordinate system, provided you are given the transformation equations. And if you are given the position vector, you can even obtain the transformation equations from them. So you can go in the reverse also. So what I am saying to you, class, is this. You can meet a coordinate system you have never heard of in an exam. And it was not an erroneous question, because the way to work on these things is consistent. So once I give you the transformation equations, I don't care. I can give you any question I like. Once provided I give you the transformation. I won't expect you to know offhand the transformation equation of parabolic symmetrical coordinates. But I would expect that if I give you the transformation equations, you can find the position vector. I also assume that if I give you the position vector, you can find the transformation equation, because it's going the reverse. It doesn't matter. If I give you one, you can find the other. If I give you the other, you can find the one. Okay, let us move forward and do something a little bit more challenging. Okay, we are given here the transformation equations, and we are given I decided to give you the differentials. The dr the xi, dr the eta, and dr the z. I don't have to give you. I can give you the transformation equations and ask you for dr the xi. I can give you. I can ask you to do that, to find that, because this is for you to write out your position vector and do the differentiation partially, and you get it. So there's nothing really hard about it. Okay. So if that is the case, I'm now trying to express the position vector in terms of E, xi, E, eta, and Ez. And again, A is the correct answer. And you can see that the way you will know is correct answer, just make the substitution and you will obtain what you had before. Just make the substitution of E xi as we have defined it, E eta as we have defined it, and you will get what we got before. So that is your proof that this is the correct answer. Now, how about the differential? How about the differential? Again, the differential is easy to do. If you have this position vector, you can get the differential. So I can give you this thing, and I can ask you for the differential without giving you these three, because this is easily obtained once you can get the position vector from the transformation and you differentiate. So don't expect me to spoon feed you by giving you these three relations, because you can find those relations on your own. Okay, so here we can again get the scaling factor for the area surface, for the surface area vectors. The surface area vectors will occur when xi is constant, eta is constant, or z is constant. And for the case where z is constant, it is the r the eta, the r the xi, the r the eta, and the cross product of these two, the n, the eta. That you got that from when we were dealing with Stokes theorem. So when you go back to your Stokes theorem, you will see this expression there. That is where we get your area vector. And if you do that, if you do that with the value of dr the eta and then dr the zeta, you will get this. You can get it either by direct, you can get it by direct product. You can get it by direct product, or you can work manually. You can work it out manually. If you work it out manually, you just take this across this, knowing that E1 cross E1 is 0, E1 cross E2 is E3, which is EZ, and E2 cross E1 is minus EZ, and E2 cross E2 is E2. So you can get it either directly, manually here, or by inspection here. This is neater because it is obvious, since the magnitude of each of these vectors is the square root of eta squared plus xi squared. It's easy to find out. So I can ask you for all of this in the objective. I'm continuing to populate the objective database constantly. So that is the area vector in the case of the constant z. We can also go ahead and find the area vectors in the case of constant eta. This is what you have in the case of constant eta. Now there's something wrong here. This should be the z. There's a copy and paste error there. So this is the z. There's a z here. Not okay. So back again. This expression is for constant eta. Then this expression is for constant xi. So those are the area vectors depending on which surface you are on. When you keep any of the coordinate surfaces constant, you get a surface. It will be difficult, it will take too much time in an objective to ask you what type of surface this is. For you to work that out and see what the surface is will take more than 2 minutes. And I do not want to give you anything that will take 3 minutes in your objective questions. So that is, I think I've gotten to the end of what I prepared. And I have like another 50 questions that will be added around these themes. Notice that I can ask you about a coordinate system you have never had before, but I either give you the transformation equations, I tell you to find the position vector, or I give you the position vector and ask you to find the transformation equations, or I just give you one of them and I ask you to find area vector or any other thing. Once you know one of those two, virtually everything else can be found, provided you follow this logic. You follow this logic where you know that you can differentiate with respect to the three variables, and then that the differential of the length differential is this quantity, whatever you get from here. So it is not a guesswork. It's not something that we just do to get. There are specific and logical steps to obtain these things. So just please bear that in mind. And so if you have, it doesn't mean, it's not necessary that you have seen the coordinate system before, but once I give you either the transformation equations on the unit or the position vector, you can get virtually every other information that you need from that. Well, I will open myself to, like I've asked the class, please go through your class rep and tell me in the last class we will have next week, our last class. Tell me if there is any, tell me this week, if there's any topic you want me to prioritize in my last lecture. So if there are things that you don't understand that you want me to take you through again or explain further, what I see as the preponderance of the request is what I'm going to take a look at. If you also put it in the chat room, where it will get to us. Anything you put in the chat room will get to us. So, because all the chats, all your answers, all your contributions are in the chat. Yes, the coordinate vector are just the differential of the. If you get the coordinate vector, you just differentiate the position vector with respect to the particular coordinate, and that will work. Even in Cartesian, it will work. If you have the position vector, you will get your I, J, and K by differentiating that position vector with respect to X, Y, or Z. And it is always correct. What's the deadline for self-tests? Well, you will get that from the office. I will take a decision on that and tell I want to take a look at I will first of all take a look at how you have been doing before I decide whether to extend it. If people have generally been doing okay, I will not extend it. But if there are people struggling, if you are struggling, please note my expression, my way of encouraging new people who are not really done well, is to just continue, go and be practicing. I want you to get good grades by practicing. And if you are practicing, you will learn more. Samuel Oketola says, is there a way to visualize the parametric plot without the use of Wolfram? Of course, there are tons of ways. I'm only using the one I know. So you go find other ways to do it. I've showed you one that I know. You can use Maple, you can write a program on your own, or you can plot it manually yourself. So there's nothing stopping you from plotting the parametric plots manually by yourself. Go and get a graph paper and plot it. Or use some other software, or program it on your own. I've given you the one that I think is easiest, but if you like hard life, go and do it in the hard way. So I'm not going to stop you. If visualizing the easy way is not acceptable to you, then you are welcome to go to do the hard things you like. Well, if there are no further questions, I will see you next week for my last class. And after taking the self-test, we usually told to go to the textbook to get answers that we failed. Well, the thing about it is that the original software was designed with a particular textbook in mind. This is a new course to me for this, for Unilag, so I have not really connected it yet. So ignore those exhortations. So you can't, those can't help you now. But if you were taking the continuum mechanics course is connected to the book that is presented. I've not been able to work that out for this course. If I have 3 months, I will probably be able to do that. It takes a lot of time to do that. Okay. The normal surface vector and the surface tangent vectors, how do we get them? The surface tangent vectors, we get them by differentiating with respect to the coordinates. Then you take the cross product of the two on the surface to get the normal to the surface. And that normal surface vector is the cross product of the two surface vectors. That's it. That's go back to the notes, go back to the slides. It's there and it's always there. It's a very simple thing. It doesn't matter whether you have seen the surface before, whether you have seen the coordinate system before, it's always correct. So what this is forcing you to do is to master your partial differentiation. Master partial differentiation, that's all. You are not to do anything serious. Just mastery of your partial differentiation. So that this is telling you to do.